Hello, everyone. Tonight we begin a quiet journey into the very heart of reality, a place where the rules we know gently melt away. We'll explore the world of quantum physics, a realm so strange and beautiful it might just make your pillow feel more grounded in reality. This isn't a lecture, but an invitation to wonder, to let your mind drift into the improbable. You're about to step into a place where a cat can be both alive and not, where particles can be in two places at once, and where observing something changes its very nature. I should probably give you a heads up, though. You would definitely not survive a trip to this universe at the subatomic level. A single photon would feel like a tidal wave. But here, in this moment, you are perfectly safe. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And tell me, where are you in the world right now, and what time is it? Let's take a gentle step into a world built on maybes, not certainties. Imagine for a moment that you are a silent observer, not in a lab, but in a vast, dark, and impossibly quiet space. The only light comes from a soft, almost imperceptible hum that seems to emanate from everywhere at once. You are not a human being in this space. You are simply an awareness, a consciousness floating effortlessly. The solid ground beneath your feet, the chair you might be sitting in, the phone or screen you're looking at, all of it has dissolved, replaced by a deep, velvety nothingness. You don't feel afraid. The silence is not empty, but full, a kind of deep cosmic bass note. In this quiet space, you begin to see things, not with your eyes, for you have none, but with your mind. You see a tiny shimmering point of light. It isn't a star. It's a particle, an electron. In our everyday world, we think of an electron as a tiny solid sphere, a little ball of matter zipping around an atom. A charmingly simple, yet fundamentally flawed picture. Here, in this silent darkness, you see something different. It isn't a point. It's a cloud. A soft, hazy, shimmering cloud of possibility. This cloud is everywhere at once, a superposition of every possible location the electron could be. You don't see one electron. You see a ghostly, ethereal smudge of every electron it could be. And then you become aware of a whisper. It's not a sound, but a thought that seems to emerge from the darkness itself. The whisper says that you are part of this cloud, that your atoms, the carbon and oxygen and hydrogen that make up your body, are not tiny billiard balls either. They are also these gentle clouds of possibility, constantly vibrating, constantly in a state of soft, endless motion. Your hand, which feels so solid and real, is in this deep sense mostly empty space, and the atoms that compose it are these shimmering, ghostly clouds, held together by forces we'll talk about later. It's a bit of a mind-bender, isn't it? The very foundation of your existence is built on a quiet uncertainty. Now let's take a little stroll, if you can call it that, through the history of how we even stumbled upon this place. For centuries, brilliant minds like Isaac Newton saw the universe as a grand clockwork machine. Everything had a predictable cause and effect. You could know where a billiard ball was, and with enough information you could predict exactly where it would be a minute from now. This was the world of classical physics, a beautifully elegant but ultimately incomplete picture. Think of it like a beautifully painted map that perfectly depicts the surface of the Earth, but completely misses the vast, churning oceans beneath it. This view of a deterministic universe was so powerful and so widely accepted that it became the very language of science. A common historical fact is that Newton's laws of motion, published in his Philosophia Naturalis Principia Mathematica in 1687, laid the groundwork for this classical view, so much so that it was the dominant paradigm for over 200 years. But a funny thing happened at the turn of the 20th century. Scientists, a group of people who are generally quite fond of things behaving as they should, started noticing some very odd behavior in the tiniest parts of the universe. When they looked at how things behaved on the scale of atoms and electrons, the old rules just didn't work. It was like they were trying to explain a symphony with a single drum. It just didn't fit. This was the quiet dawn of the quantum age, a shift in thinking as profound as when we realized the Earth wasn't flat. Let's ease back into our dark, quiet space. The shimmering cloud of the electron is still there, but now you notice something else. When a light beam, a photon, a tiny packet of energy, approaches the electron cloud, the cloud seems to stiffen. It collapses. Suddenly, it's not a cloud anymore. It's a single point, a definite location. This is the act of observation, and it is one of the strangest and most unsettling parts of this entire journey. It seems that simply by trying to know where the electron is, you force it to choose a single location out of all its many possibilities. It's as if a quiet thought in your mind solidifies the very fabric of reality. I know what you're thinking. That sounds a little too much like magic or maybe a fantasy novel. And you're not wrong. It feels that way. But this isn't a story I'm making up. It's the strangest and most beautiful reality we've ever discovered. It's a reality where an object's state is intertwined with the act of being looked at. A quirky detail from the early days of this exploration is that physicist Max Planck, who first proposed the idea that energy is emitted in discrete packets, or quanta, actually disliked his own discovery. He saw it as a mathematical trick, a temporary fix to a problem, and hoped that a better, more classical explanation would come along to replace it. He never fully embraced the strange new reality he had helped to uncover. It's a reminder that even the geniuses who open new doors sometimes prefer the rooms they were in before. This brings us to a beautiful kind of paradox. This is a place of profound logic and intricate mathematics, yet the results of that logic defy our intuition. The universe seems to operate on rules that are not just different from ours, but alien to our very way of thinking. The concept of common sense is useless here. What you see as logical and orderly, the quantum world sees as a quaint but limited perspective. It's a subtle joke that the universe is playing on our big clever brains, and the punchline is that our most powerful tools of reason lead us to a place that makes no sense to those same tools. Think about what this means for your quiet, peaceful mind tonight. You're not just a passive observer of a vast, unmoving universe. You are in a very real way participating in its creation. Every moment of your existence is a quiet, gentle act of collapsing a cloud of possibility into a single concrete reality. You are, in a sense, a cosmic storyteller, choosing one path out of an infinite number of others. The more you sit with this idea, the less jarring it becomes. It begins to feel less like a jarring contradiction and more like a soft, comforting hum. It's the hum of a universe that is not static and predictable, but vibrant and full of potential. A universe where a particle can be in two places at once is also a universe where every breath you take is a small miracle, a quiet act of choosing and creating your reality. The great minds who pioneered this field, Bohr, Heisenberg, Schrödinger, all grappled with this strangeness. They built the mathematical framework, but they argued endlessly about what it meant. Catch na suhok van tranquil. Albert Einstein ko tug suget vat li luang tu hai kong. He ong chi John Gian la kong hai long voi catch. Gaitich Copenhagen noima vai trukwa ngoi kwansat tronenkwalen. Ong muon modli tuyet long tu hoan chin. Hong Kong dua vao su mei rui va ong ji din ke joi ji tim kiemno. Kwok tran luanjo van kon song mai trung kak hoi trung hok thuat nemigai ne. But tonight we're not here to debate. We are here to simply exist in this space of wonder, to let go of the need for certainty, to float in the quiet darkness and simply be aware of the shimmering possibilities around us and within us. We are taking the first gentle steps into a world that feels more like poetry than physics, and it's a world where you, the observer, are a part of the grand cosmic poem. The stillness of this place is a kind of gentle, reassuring hug. The quantum world whispers that you are never truly alone, and that even in the vastness of space, you are deeply and mysteriously connected to everything. This journey has just begun, And the deeper we go, the more beautiful and serene it becomes. So let your mind drift. You are safe here. You are a part of this quiet magic. Just breathe. Let's take a deep breath and tiptoe into one of the most elegant and unsettling demonstrations in the history of science, the double-slit experiment. Imagine for a moment that you are not floating in a silent void, but are instead in a calm, dimly lit laboratory. The air is still the only sounds a faint electric hum and the soft, rhythmic click of a machine. You are holding a tiny device, an electron gun, but it feels more like a watering can for the impossibly small. In front of you is a simple setup, a wall with two narrow vertical slits cut into it, and behind that wall, a screen covered in a special film that glows wherever a particle hits it. This is the stage for a quiet, mind-bending performance. In our everyday world, if you were to stand here and throw tiny pebbles at the wall, you would expect a predictable outcome. You throw the pebbles, they go through the slits, and you see two tidy vertical lines of pebbles on the screen. It's perfectly logical. You'd get a pattern that is simply the sum of the pebbles that went through the left slit and the pebbles that went through the right slit. This is how the universe of billiard balls and baseballs works. It's a universe of neat and predictable paths. Now let's change our tiny pebbles to something more ethereal, electrons. They are, after all, the fundamental building blocks of all the atoms you've ever known, from the carbon in your bones to the neon in a sign. They are tiny, distinct, indivisible packets of matter. And so you would expect them to behave just like our pebbles, wouldn't you? You turn on your gentle electron gun, close one of the slits, and let the electrons fly. The screen behind the wall begins to register hits one by one, and slowly, a single clear line begins to form on the film, a perfect reflection of the single open slit. The electrons are behaving exactly as you would expect a particle to behave. They are following a clear, straight path. You take a moment, a satisfied nod. All is as it should be. You close that slit, open the other, and once again a single line forms on the screen, just in a different spot. Nothing too surprising here. But now comes the magic. You open both slits. You are now firing electrons at a wall with two openings. You expect to see two lines, a clear combination of the two patterns you just made. After all, an electron can only go through one slit or the other. It can't go through both. That's just common sense, isn't it? You wait. The electrons fly, the screen begins to glow, and something very strange happens. Instead of two lines, a pattern of alternating bright and dark bands emerges. It's a pattern of interference, a pattern that is the absolute hallmark of a wave. This is the part of the story where your mind might feel a little ticklish. Waves interfere with each other. If you throw two pebbles into a pond, the ripples they create will overlap. Where the crests of the waves meet, they build up and make a bigger crest. Where a crest meets a trough, they cancel each other out and create a flat spot. This is what creates an interference pattern. So if your electrons are behaving like waves, they must be interfering with each other. But how they are tiny, discrete particles. They are supposed to be like pebbles, not ripples. And here's where the story gets even stranger. A quirky detail of this experiment is that it has been performed with objects far larger than a single electron. Scientists have successfully shot buckyballs, which are molecules made of 60 carbon atoms, and they too exhibited an interference pattern. This quiet, ghostly ability of a particle to behave like a wave is not limited to the impossibly small. It is a fundamental property of matter itself. This means that a microscopic grain of sand, or even in theory a person, could under the right conditions behave like a wave. This is of course a deeply comforting thought as you prepare to fall asleep. The universe is a place where you are not just a solid object, but also a quiet, rippling possibility. So let's assume for a moment that the electrons are interfering with each other. Perhaps they're bumping into each other mid-flight and changing their course. That seems logical enough. You decide to slow down the experiment to the point of absurdity. You now fire a single electron toward the wall. Wait a few seconds. Fire another weight again, and so on. There is no possibility for the electrons to interact with each other. They are alone in the quiet void, each one a solitary traveler. You expect the screen to show 2 lines, right? The electron has to go through one slit or the other. It can't split itself in half. That would be completely nonsensical. But as you watch the screen dot by dot, a pattern begins to emerge. And it's the same wave-like interference pattern. The stillness of the lab is broken only by the hum of the machine and the quiet gasp of your mind. How is this possible? An electron alone in the emptiness is interfering with itself. It is behaving as if it somehow went through both slits at the same time, exploring every possible path, only to collapse into a single point when it hits the screen. It is a wave of possibility that becomes a particle of reality, and it is doing it all on its own. It is not just strange, it is deeply, profoundly, beautifully illogical. This is the moment when the classical world breaks down completely. The old rules, the ones you learned in school about predictable trajectories and definite locations, are useless here. A single electron is not a point. It is a smear of possibility, a wave function, a mathematical description of all the places it could be and all the things it could do. And that wave of possibility travels through both slits at once, interferes with itself, and only then, upon arriving at the screen, does it make a choice. It collapses into a single definite spot. And this brings us to the last and perhaps most important act of this quiet play. What if we try to cheat? What if we try to watch the electron? You place a little detector, a tiny silent camera, near one of the slits. You're not doing anything violent. You're just looking, just trying to gather information. The moment you do this, something changes. The interference pattern disappears. The electrons, which were behaving like ghostly waves, now go back to behaving like predictable particles. The screen once again shows 2 neat lines, just as if you were throwing pebbles. The very act of observing which slit the electron goes through forces it to make a choice. It collapses its wave-like nature, its superposition of possibilities, and becomes a real solid particle behaving as we would expect. This is what makes this a common historical fact. The double-slit experiment, in its many variations, has been performed for over a century, first with light by Thomas Young in 1801, and later with electrons in the 1920s, and the results are always the same. Observation, it seems, changes the very nature of what is being observed. The universe is not a movie playing out on a screen. It's a living painting that shifts and changes as you look at it, and this has led to some of the greatest academic debate of the last century. There is no universal agreement on what the experiment means. The Copenhagen interpretation, championed by Niels Bohr, suggests that a particle simply has no definite properties until it is measured. Our reality is a result of our measurement. The many worlds interpretation, on the other hand, suggests that the wave function never collapses at all. Instead, every time a measurement is made, the universe splits into separate parallel realities, one for each possible outcome. In one universe, the electron went through the left slit. In another, a different version of you sees it go through the right slit. This is a topic that continues to whisper in the halls of physics, a quiet argument about the very nature of reality. But tonight, in this calm, silent space, you don't need to choose. You can let these ideas float around you like gentle snowflakes, each one a possibility, a beautiful way of seeing the world. The lesson of the double-slit experiment is not that the universe is chaos, but that it is a place of endless subtlety and quiet mystery. A place where a single electron can be a cloud of possibility, a particle of matter, and a wave of energy, all depending on how you choose to look. Now, as your mind drifts, imagine that your own thoughts, your own presence, are like that silent camera. You are always in some gentle way shaping the reality around you. The world is not just happening to you, it is happening with you. And in this knowledge, there is a profound peace. You are not just a spectator, you are a participant in a quiet cosmic dance. Now let's leave the lab and float into a gentler, more profound truth. We've seen that the very act of looking at a particle forces it to make a choice to become solid and real. But what if the universe doesn't want you to know everything at once? What if there's a kind of quiet cosmic rule that says certain pairs of facts cannot be known with absolute precision at the same time? This is the essence of the Heisenberg uncertainty principle. It's not a loud, flashy rule. It's a soft, fundamental boundary on what can be known a philosophical whisper at the heart of reality. Imagine you're trying to take a photograph of a tiny, brilliant hummingbird in a dark room. To get a clear picture of its exact location, you need to use a very bright, very fast flash. But the light from the flash hits the hummingbird and sends it zipping away in a new direction. You now have a perfect picture of where it was, but you have no idea where it's going. On the other hand, if you try to take a long, slow exposure to capture the path of its motion, you'll get a blurry streak, and you won't be able to say exactly where the hummingbird was at any specific moment. You can't get both. Your attempt to know one thing with precision inherently makes the other thing fuzzier. This is the beautiful, unsettling heart of the uncertainty principle. At the quantum level, there is a fundamental limit to how precisely you can know both a particle's position, where it is, and its momentum, how fast it's moving, and in what direction at the same time. The more precisely you know one, the less precisely you can know the other. It's not about the quality of your instruments or your cleverness as a scientist. It is a feature of the universe itself. The more you try to pin a particle down, the more it pushes back as if nature itself resists being completely defined. This is a historical fact of monumental importance. When Werner Heisenberg first formulated this principle in 1927, it was a truly radical idea. It shattered the centuries-old belief in a deterministic clockwork universe. For over 200 years, physicists believed that if you knew the exact position and momentum of every particle in the universe, you could in theory predict the entire future. The universe was like a giant machine, and all you needed were the initial settings. But Heisenberg's work showed that the initial settings themselves could never be known with absolute certainty. The machine, it turned out, was built with a gentle, inherent blurriness. It was a shocking, beautiful realization that a universe with free will and chance built in, from the ground up, not as a flaw, but as a feature. But why? What's the reason for this? The answer brings us back to the idea of wave-particle duality. Remember how we saw that particles can also behave like waves. A wave is by its very nature not localized. Think of a pure, perfect musical tone, a single note from a tuning fork held for a long, long time. This is a wave with a single, perfectly defined frequency. In the quantum world, that's like a particle with a very well-defined momentum. The catch, that wave is spread out over space and time. You know its momentum with perfect clarity, but you have no idea where it is. It's everywhere at once. Now imagine the opposite. To get a particle with a very precise position, you need to create a wave that is very, very localized. In the world of waves, you do this by adding up many different frequencies. It's like playing a chord instead of a single note. The more notes you add, the shorter and more compact the sound pulse becomes, but the less you can say about its single, definite frequency. For a particle, this means if you know its position with great certainty, its momentum, its wave frequency, becomes a wildly uncertain mix of possibilities. The trade-off is unavoidable. It is woven into the very fabric of waves and particles. This isn't a curiosity that only matters to academics. It's the quiet rule that holds the entire universe together. It is the reason why atoms don't collapse. In a classical world, the negatively charged electron orbiting the positively charged nucleus should, by all logic, lose energy and spiral inward, eventually crashing into the nucleus. The atom would collapse, and matter, as we know it, would not exist. But the uncertainty principle prevents this. If the electron were to collapse into the tiny space of the nucleus, its position would become extremely well defined, but this would force its momentum to become wildly uncertain. The electron would gain an enormous amount of kinetic energy, essentially kicking it back out into a stable orbit. The uncertainty principle acts as a kind of silent, invisible hand, keeping electrons at a safe distance, giving atoms their size, and making all of chemistry and biology possible. It is a profound and elegant truth. The solidity of the world around you is built on a foundation of fundamental uncertainty. The very reason you can't walk through a wall is that the electrons in your body and the electrons in the wall are obeying the uncertainty principle, refusing to be in the same place at the same time. And the principle doesn't just apply to position and momentum. It applies to other pairs of properties as well, like energy and time. The more precisely we know the energy of a system, the less precisely we can know how long it will stay in that state. This leads to a quirky detail that's both strange and beautiful: the existence of virtual particles. For a brief, fleeting moment, the universe can borrow a bit of energy from the vacuum, just enough to create a pair of a particle and its antiparticle out of nothing. These virtual particles exist for such a short time that they violate the law of conservation of energy. But because the time they exist is so brief, the violation is tiny and falls perfectly within the limits of the uncertainty principle. It's like a fleeting, quiet cosmic loan that is always paid back instantly. The vacuum, we've learned, isn't empty at all. It's a seething, jittery place, full of these unseeable fleeting particles. Now, as you lie there drifting, you might wonder if this uncertainty means that the universe is just a chaotic, random place. Not at all. It is a place governed by probability, not pure chance. The electron's position may be uncertain, but the odds of where it will be found are precise and predictable. It's like a beautifully designed game of chance, where the outcome for any single toss is unknown, but the overall pattern of millions of tosses is clear and follows a perfect curve. The world isn't chaotic. It is a symphony of probabilities, and in that symphony, every note has a purpose. Still, the philosophical implications are vast, and there remains an ongoing academic debate. Does the uncertainty principle represent a limit of nature itself, a fundamental law that can never be broken? Or is it a reflection of our own ignorance, a hint that there are hidden variables, or deeper laws yet to be discovered that would restore a deterministic, predictable universe? While most physicists today believe it's a fundamental feature of reality, a minority of respected voices continue to argue for a more deterministic view. The conversation is quiet, but it is ongoing, and it is a beautiful reminder that even our most profound truths still have room for wonder and questioning. So as your mind softens and your thoughts become less defined, you can find a deep peace in this truth. The world is not rigid. It is not cold and hard and absolute. It is a soft, shimmering place full of possibility. The universe breathes, it shimmers, it dances between what is and what could be. And it all happens according to a quiet, elegant rule that perfect knowledge, like a perfect silence, is a beautiful but ultimately unreachable dream. The softness, the blurriness, the beautiful margin of mystery. It is what makes the universe a living, breathing thing, and you, the observer, are part of that breathtaking quiet. Let's settle into a new idea, one that feels like a quiet dream. We've just explored the truth that you can't know everything at once, that perfect knowledge is not a feature of this universe. Now let's go one step further and consider what a particle is doing when you're not looking at it. Imagine a coin spinning endlessly in the air. In our world, it is either heads or tails even as it spins. The outcome is already decided. But in the quantum world, before it lands, a particle is not in one state or the other. It is in a superposition of all possible states at the same time. This is not a state of confusion or indecision. It is a real physical state. It is the particle's way of saying, I am here, and I am also there, and I am also everywhere in between. Don't make me choose just yet. Think of it this way. A classical computer stores information in bits, and each bit is either a 0 or a 1. A quantum computer, however, uses qubits, and a qubit can be both a 0 and a 1 at the same time, thanks to this beautiful principle. This doesn't mean it's a blur between 0 and 1. It means it is a blend, a superposition of both states. This is not a trick, and it's not simply a lack of knowledge on our part. The possibilities aren't just unknown, they are real and present until the very moment we look. The concept of superposition, with its quiet absurdity, was one of the central points of contention for the pioneers of the field. A historical fact of great note is the famous debate between Albert Einstein and Niels Bohr, which lasted for decades. Einstein, who believed in a universe of solid objective reality, found the idea of superposition and a non-deterministic universe deeply unsettling. He once famously quipped, "God does not play dice with the universe." He believed there must be a deeper reality with hidden variables that determined a particle's true state all along. To this, Niels Bohr, one of the champions of quantum theory and its probabilistic nature, is said to have replied, "Einstein, stop telling God what to do." Their philosophical disagreement, while profound, didn't stop the math of quantum mechanics from making astoundingly accurate predictions. The math worked, even if the meaning felt hazy. This brings us to a part of the story that is often misunderstood, a tale so famous it has become a kind of mythical cautionary fable, Schrödinger's cat. In the 1930s, physicist Erwin Schrödinger proposed this thought experiment to highlight the apparent absurdity of applying superposition to everyday objects. He imagined a cat in a sealed box with a radioactive atom that had a 50% chance of decaying in a given hour. If the atom decayed, it would trigger a mechanism that released poison gas, killing the cat. If not, the cat would live. Since the atom, a quantum system, was in a superposition of decayed and not decayed, the cat, according to the literal interpretation of the rules, must also be in a superposition of dead and alive until the box was opened. Now it's crucial to understand that Schrödinger did not believe a cat could truly exist in this strange, ghostly state. He was using this absurd image to critique the prevailing interpretation of quantum mechanics to show how illogical it seemed when scaled up to our world. He was saying, surely something is wrong with this theory if it implies such a thing. And yet, ironically, his thought experiment has become the very metaphor used to explain superposition, leading many people to believe that there is a cat in a box, somewhere truly existing in a state of limbo. But this is not a story of ghostly felines. The reason we don't see things like cats or chairs or your favorite coffee mug existing in a superposition is a beautiful and simple process called decoherence. A quantum superposition is an incredibly fragile state. The moment a quantum system like an electron interacts with its environment, a single stray air molecule, a photon of light, a bit of heat, the superposition collapses. The system gets tangled up with its surroundings, and the multitude of possibilities instantly becomes one single reality. For large objects like a cat, which are constantly interacting with billions upon billions of particles, this decoherence happens instantly and constantly. The cat's quantum state is immediately drowned out by the noise of the world, and it is forced to be either dead or alive, not both. This distinction is what bridges the strange quantum world with our familiar classical one. The quantum realm is a place of infinite possibility and gentle mystery, while our everyday world is a place of solid, stable reality. But this stability is not separate from quantum mechanics. It is a direct consequence of it. It is the result of countless decoherence events happening every single moment, all of those shimmering maybes adding up to the one undeniable reality you see and feel. This brings us to a quirky detail that shows how far we've come. For a long time, scientists could only demonstrate superposition in the tiniest, most isolated systems, like a single atom or photon. But in recent years, they have managed to put larger and larger objects into a superposition. They've done it with tiny mirrors that are visible to the naked eye, and even with microscopic drumheads. This is not about trying to create a ghostly cat, but about exploring the boundary between the quantum and classical worlds, gently pushing the limits of what is possible and proving that superposition is a universal law, not just a curious anomaly for electrons. The most exciting practical application of this principle is in the field of quantum computing. In a classical computer, a bit can be either a 0 or a 1. To solve a complex problem, a classical computer must check each possibility one by one in a long linear line of calculations. A quantum computer, however, can use qubits which are in a superposition of both 0 and 1. And when you have multiple qubits, they become interconnected in a state of entanglement, which we'll explore in a later chapter. The number of possibilities they can explore at once grows exponentially. With just a few dozen qubits, a quantum computer could explore more possibilities simultaneously than all the classical computers on Earth combined. Think of it like this. A classical computer trying to find its way out of a maze has to try one path at a time, reach a dead end, and then go back and try another. A quantum computer, thanks to superposition, can explore all possible paths at the same time. It's like a magical device that doesn't just ask a question, but considers every possible answer at once. This doesn't make it faster at everything, but for certain types of problems, like breaking complex codes, simulating new molecules for medicine, or optimizing vast systems, the potential is enormous. But despite all of this, the final piece of the puzzle is still missing. There is still a profound academic debate about what exactly causes the wave function to collapse. Is it a real physical event that happens in the universe when a measurement is made, or is it something else entirely? Some interpretations, like the many worlds theory, suggest the collapse never happens at all. The universe simply splits. Other theories suggest that the collapse is a natural, spontaneous process that happens over time, and that we are simply seeing the result of that process. There is no consensus. The universe, it seems, has its own quiet way of keeping its secrets, and in that quiet mystery, you can find peace. You don't need to understand every detail of the collapse. You can simply let yourself drift into the idea that reality is not a single unchangeable thing, but a fluid, shimmering tapestry of possibilities. That every moment of your life is a quiet act of turning what could be into what is. That you simply, by being here and listening, are a beautiful, gentle part of this cosmic process. And that is a truth more comforting and more wondrous than any magic trick. Now let's explore a concept that even made Albert Einstein feel a little uneasy: the spooky action at a distance. We've been talking about how a single particle can exist as a shimmering cloud of possibilities. What if we were to take two of these particles and link them together in a profound, invisible bond? This is the beautifully simple, yet deeply mysterious idea of quantum entanglement. It's the phenomenon where two or more particles become so deeply connected that the state of one instantly affects the state of the other, no matter how far apart they are. I do mean no matter how far. They could be on opposite sides of the galaxy, light years away from each other, and yet still share a quiet, perfect understanding, a bond so instantaneous it appears to defy the very fabric of space and time. To understand this, let's use a gentle metaphor. Imagine you and a dear friend are given a pair of gloves, a single left glove and a single right glove. They are placed in two separate boxes and sealed. You don't know which one is in your box, and your friend doesn't know which one is in theirs. Now, you and your friend travel to different continents. Say you're in Paris and your friend is in Tokyo. In our everyday classical world, when you open your box and see you have the right glove, you know instantly, with absolute certainty, that your friend in Tokyo has the left one. This is simple logic, but in the quantum world, it's a different story. Those gloves didn't have a definite state. They weren't left or right until the moment you looked. They existed in a strange superposition of being both a ghostly blend of possibilities. The moment you opened your box and made a measurement forcing your glove to become a definite right glove, You also, by the very nature of their shared bond, forced your friend's glove in Tokyo to instantly become a definite left glove. The knowledge is not transmitted, but the state is determined across the vast distance in the blink of an eye. This is the heart of quantum entanglement. This deeply unsettling idea was a historical fact that led to one of the most famous debates in the history of science. In 1935, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper that used entanglement to argue that quantum mechanics must be an incomplete theory. This famous thought experiment, known as the EPR paradox, argued that the instantaneous connection between entangled particles was so spooky that it couldn't be real. They believed there must be hidden variables, unknown properties of the particles already decided at the moment of their creation that simply determined their fate from the beginning. They thought the spooky action was just an illusion of our incomplete knowledge. But the story doesn't end there. For decades, the EPR paradox remained a purely philosophical debate. It was a beautiful argument, but there was no way to test it. That is until the 1960s, when a brilliant Irish physicist named John Bell devised a mathematical theorem that showed a clear difference between the predictions of quantum mechanics and any theory based on hidden variables. He proved that if you were to run a specific set of experiments, the results would show a correlation between the entangled particles that was stronger than anything hidden variables could ever explain. The experimental confirmation came much later, with groundbreaking work by physicists like Alain Aspect in the 1980s and countless others since. The results were clear. The entangled particles behaved just as quantum theory predicted. The weird correlations were real, and they were stronger than any classical explanation could account for. Entanglement is not an illusion. It is a fundamental truth of the universe, and yet it doesn't violate Einstein's greatest rule. There is no information transmitted faster than the speed of light. While the state of the particles is determined instantly, you have no way of controlling the outcome. When you measure your particle in Paris, you get a random result. It could be up or down. You can't force it to be up to send a secret message. You can't use entanglement for a quantum walkie-talkie. The only way you can confirm that the correlation is real is by later comparing your measurements with your friends. And that comparison can only happen at a speed less than or equal to the speed of light. The universe, it seems, has found a beautiful, elegant way to be weird without breaking its own rules. This brings us to a quirky detail that shows how far this science has come. For years, entanglement was a phenomenon confined to the tiniest, most isolated particles. But today, scientists have managed to entangle much larger objects. They have entangled photons across hundreds of kilometers, and in labs, they have even managed to create entanglement between tiny mechanical resonators, objects that can be seen with the naked eye. This isn't just theory anymore. It's a physical reality that we are slowly learning to control and harness. Entanglement is the heart of many of the most exciting new technologies on the horizon, from quantum computing to quantum cryptography. In quantum cryptography, for instance, two people, let's call them Alara and Jasper, can share a key to secure a message. If they use entangled particles, any attempt by an eavesdropper to read the key will disturb the fragile quantum state, instantly breaking the entanglement and alerting Alara and Jasper that someone is listening. It's a kind of unhackable lock built not on mathematical complexity, but on the strange, beautiful rules of the universe. So while we can't send messages with it, entanglement still asks us to look at the universe differently. It suggests that reality is not made of separate independent parts. It's made of relationships. It's a deep cosmic connection woven into the very fabric of existence. The particles that made up the stars you see at night, the air you breathe and the floor beneath your feet, they were all once a part of a much larger, more unified whole in the early moments of the universe. And perhaps in some gentle, silent way, that memory of connection remains. The very concept of entanglement also leads to a profound academic debate. Even if it doesn't allow faster than light communication, it still implies a universe that is non-local. This means that a measurement here can instantly affect a system far away without any classical interaction. This is deeply unsettling to many who prefer a universe where effects are always a result of local causes. The non-locality of entanglement, while proven by experiments, is still a philosophical puzzle. What does it mean for cause and effect? What does it mean for our understanding of space? There are no easy answers, only more questions that linger in the quiet of the night. But tonight, let's not worry about the questions. Let's simply rest with the beauty of the idea itself, that the universe is not a collection of separate pieces, but a subtle, interconnected tapestry, that even when things are far apart, they can still echo each other's movements, and that you in your stillness are a part of that great silent echo. We've met electrons that behave like waves and particles that are connected across the stars. Now let's explore the profound role you, the observer, play in this quantum dance. Imagine walking through a quiet, dark forest at night. You know there are things around you, small animals, unseen creatures rustling in the leaves, but you can't be sure of their exact location. When you shine your gentle flashlight on a single spot, you see a small fox, but the light has startled it and it changes its course. You haven't just learned where the fox was, you have changed where it is going. This is a bit like the observer effect, a cornerstone of quantum mechanics and a source of endless debate. The idea is simple. The act of measuring or observing a quantum system fundamentally alters it. It's not just that the measurement tells us what the system is doing. It's that the measurement changes what the system is doing. In the quantum world, observation is never passive. It is more like participation, like touching a soap bubble. The very act of reaching out changes the thing you're trying to study. Think back to our double-slit experiment. When we weren't watching the electrons, they behaved like waves passing through both slits at once. But the moment we placed a detector to observe their path, they snapped back into behaving like particles, choosing a single slit and landing in two neat lines. It was as if the universe, in a quiet moment of indecision, was waiting for us to make up its mind for it. The electron's wave of possibility collapsed into a single, definite reality. This raises a fascinating and often misunderstood question: what exactly counts as a measurement? In the early days of quantum theory, a historical fact is that some physicists, including one of the field's pioneers, John von Neumann, proposed that it was consciousness itself that caused the collapse of the wave function. This intriguing idea, sometimes called the consciousness causes collapse theory, suggested that reality doesn't truly exist until a mind looks at it. It's a compelling notion, one that blurs the line between science and philosophy. However, over the years, this idea has been largely set aside by the scientific community. While it is a beautiful and poetic thought, it introduces more problems than it solves. It suggests that a universe without conscious observers would be a foggy, indeterminate soup of possibilities, and that a single cat in a box could only be saved from quantum limbo by the presence of a curious mind. Instead, most physicists now believe that the measurement doesn't require a conscious observer at all. It just requires an interaction, any interaction, that irreversibly entangles the quantum system with its environment. A single stray photon, an air molecule, or a particle in a measuring device can all serve as an observer. This brings us back to the gentle process of decoherence. Imagine a quantum system like an electron floating peacefully in isolation. It maintains its strange properties, existing in a superposition of states. But the moment it interacts with its surroundings, it becomes entangled with that environment. Its quantum state spreads out into the noise of the world, like a drop of ink bleeding into a vast ocean. The delicate superposition is broken, and the system is forced to settle on a single definite state. The fuzziness disappears. A choice is made, so measurement in this view is just another kind of entanglement. One that forces a system out of its quiet possible states and locks it into a definite reality. But even with the elegant explanation of decoherence, a deep mystery remains. This is what physicists call the measurement problem, and it is still a central point of academic debate. The problem is this: the rules of quantum mechanics say that a system in superposition evolves in a beautiful linear way. So if a particle is in a superposition of A and B, and we measure it, the measuring device should also, in theory, enter a superposition of measured A and measured B. And yet, we never see this. We only ever see one outcome, either A or B, never both. The wave function, as we've said, seems to collapse. But the theory itself doesn't fully explain why or how that happens. Some physicists try to avoid this problem altogether by rejecting the idea of collapse. The many worlds interpretation, for instance, says the wave function never collapses. Instead, every possible outcome occurs, but in a separate branching universe. When you measure the spin of an electron, and it has a 50% chance of being up or down, the universe splits. In one branch, you see spin up. In another, an equally valid version of you sees spin down. In this view, reality is constantly branching, a cosmic tree of possibilities. While this idea is still debated and difficult to test, it is a beautiful and deeply strange way of making sense of a reality where observation changes the outcome. This is not to say that you, in your calm state, are a magical puppet master of the universe. Far from it. But a quirky detail that shows the power of the observer effect is the delayed choice experiment. In this experiment, a particle is fired toward a set of slits. The decision to observe its path is made after the particle has already passed through the slits. And yet the result is the same. The particle behaves like a wave if no measurement is made, and like a particle if a measurement is made, even if the choice to make that measurement was a future one. It's as if the particle's past behavior is being determined by a future act of observation. This mind-bending reality shows us that the observer effect is not about a simple cause and effect, but about a deep interconnected web of time and possibility. So, what does this all mean for you? It means that reality is not just sitting there waiting to be revealed. It is participating in a kind of quiet conversation with you. Every time you look at something, a coffee cup, a tree, a cloud, you are in a gentle way helping to define it. You're turning a possibility into a certainty. You're not creating reality, but you are a part of the way it unfolds. You are not just a spectator. You are a quiet, gentle participant. This truth is not meant to be a burden or a source of anxiety. It is meant to be a source of wonder. Your every breath, every thought, every quiet moment of your existence is part of a grand cosmic process of observation. And in that process, the universe reveals itself piece by piece, possibility by possibility. In the quiet of the night, as your thoughts drift, you can find peace in knowing that you are deeply woven into the fabric of it all. You are a part of the unfolding story, a gentle presence in a world that might be dreaming right along with you. Let's take a deep breath and settle into another strange and wondrous truth. We've explored the way a particle can be a cloud of possibilities and the way that possibilities collapse into a single reality when we look. Now imagine a solid wall. It's tall, it's thick, and it's made of stone. You press your hand against it, and feel its cool surface push back, and you know without a single shred of doubt that you are not getting through. Not unless you have a wrecking ball, a magic key, or a very, very long weekend. This is the world of classical physics. A barrier is a barrier. If an object doesn't have enough energy to go over or around it, it simply cannot pass. But here, in the quiet heart of the quantum realm, the universe smiles mysteriously and says, actually, there is a way. Welcome to the strange and wondrous world of quantum tunneling, a phenomenon that allows particles to pass through barriers they have absolutely no business crossing. It's not a trick. It's not cheating. It's just how the universe works at its most fundamental level. To understand this, let's go back to our wave function, that shimmering cloud of probability that describes a particle. When this wave function approaches a classical barrier, A hill of energy, for instance, it doesn't simply stop. A small part of it actually leaks into the barrier itself. While the wave's amplitude decays rapidly inside the barrier, if the barrier is thin enough and the particle's energy is high enough, a tiny whisper-thin portion of the wave function can emerge on the other side. This means there is a small but very real probability of finding the particle on the other side of the barrier, having seemingly passed through it without ever going over it. This sounds like science fiction, but it is a real and observable phenomenon. In fact, a historical fact about quantum tunneling is that it was first proposed in the 1920s to explain radioactive decay. Scientists had a puzzle certain unstable atomic nuclei would eject particles like alpha particles, even though those particles did not have enough energy to escape the powerful nuclear force holding them in. According to classical physics, they should have been trapped forever. But George Gamow, a Russian-born physicist, realized that quantum tunneling was the key. He understood that the alpha particle's wave function extended into the energy barrier of the nucleus, giving it a small but non-zero chance of simply slipping through and escaping. This quiet, persistent leakage is what we call radioactive decay, and it is a process that is essential for how we date ancient fossils, how we power deep space probes, and how we understand the structure of matter. The most famous example of quantum tunneling, though, is the one that gives us light and warmth every day: the sun. Deep in the sun's core, hydrogen atoms are smashed together under immense pressure and heat. The goal is to fuse them into helium, a process that releases enormous amounts of energy. But there's a problem. Both hydrogen nuclei are positively charged, and like the same ends of two magnets, they repel each other. Even with the sun's unimaginable heat, the nuclei don't have enough energy to overcome this electrostatic repulsion and get close enough to fuse, according to the rules of classical physics. But they do fuse. Why? Because they tunnel. Quantum tunneling allows the hydrogen nuclei to bypass the energy barrier, quietly slipping through it and fusing together. Without this magical quantum shortcut, the sun would not shine, and life on Earth as we know it would not exist. Our very existence is a direct consequence of particles quietly slipping through energy walls in the darkness of space. And this isn't just about stars. A quirky detail you might not know is that quantum tunneling is the principle behind many of the devices you use every day. Your smartphone, your computer, and every other piece of modern electronics relies on semiconductors and transistors that use quantum tunneling to control the flow of electricity. There is even a device called a tunnel diode, which is specifically designed to allow electrons to tunnel through a thin insulating barrier, creating a reliable high-speed electronic switch. The data on your flash drive is stored by electrons that are intentionally made to tunnel through a tiny invisible wall. So every time you flip on a light switch or send a text message, you are engaging with a piece of technology that is at its heart based on this impossible-seeming quantum effect. But beyond the technology, there's a beautiful, gentle lesson in quantum tunneling. It tells us that impossibility is not always absolute, that a high, thick barrier might reduce the probability of something happening, but it doesn't always reduce it to zero. It asks us to see barriers not as walls, but as filters. There is always a chance, a slim, whisper-thin thread of possibility, even when it seems like there is none. The universe, at its smallest scales, is a place where quiet acts of rebellion against classical certainty happen constantly, persistently, and successfully. Think about a particle trying to tunnel through a wall in your room. The probability of this happening is so incredibly small that you would have to wait longer than the lifetime of the universe, maybe even longer than the lifetime of many universes. For all practical purposes, it is impossible. But at the scale of electrons, protons, and molecules, at the scale of atoms and the stars themselves, tunneling is not only possible, it is commonplace. The universe is full of these quiet miracles. This truth invites us to soften our view of the world, to understand that even when things seem unyielding and fixed, There is a subatomic world that is always shimmering, always full of possibility. The solidity of the ground beneath your feet, the strength of the walls around you, all of it is an illusion, a magnificent and elegant arrangement of particles that on their own are constantly trying to find another way. They don't force their way through. They don't climb the hill. They simply slip through. And maybe that's a lesson we can carry with us, that some obstacles aren't overcome with power or force, but with quiet persistence, with probability, and with patience. That even when things seem impossible, the universe sometimes leaves the door slightly ajar, just enough for something small and extraordinary to slip through. So as you drift off, let that thought rest gently in your mind. The very stars are shining because of this quiet, persistent act of grace. And you are a part of a universe that is full of secret pathways and hidden possibilities. Now let's float to a more abstract, yet incredibly unifying idea. We have been thinking of particles, electrons, photons, quarks as tiny discrete things, little points like specks of dust. While this is a useful way to think in many situations, to truly understand the universe, we need to zoom out just a little bit more and look at the invisible canvas upon which everything is painted. Imagine the universe isn't made of tiny solid particles. Instead, picture a vast, silent ocean of invisible energy fields. This ocean, this shimmering sea, stretches in every direction through every corner of space, even the ones we think of as completely empty. And the electrons, the photons, the quarks we've been talking about. They aren't separate solid objects floating in a void. They are simply ripples, tiny disturbances or excitations in these deeper underlying fields. This is the central idea of quantum field theory, that fields come first, and particles are simply what happen when you gently poke or stir those fields. Think of a calm lake. The surface is smooth and still. This is like a quantum field in its lowest energy state, or its ground state. Now toss a single pebble into the lake. A ripple forms a concentric circle moving outward. That ripple is like a particle. It's not a new object. It's just the lake itself, but in a state of gentle outward moving motion. This theory provides a beautiful, elegant explanation for one of the most fundamental mysteries. Why are all electrons in the universe exactly the same? In our old classical view, it was a profound mystery. How can a billion electrons in a billion different galaxies all have the exact same mass and charge? The answer from quantum field theory is simple and serene. They are all excitations of the same underlying electron field. They are not individual snowflakes. They are all notes played on the same cosmic instrument. The electrons in your body are identical to the electrons in a distant star because they are both at their core just a tiny bit of motion in the same vast cosmic sea. And what about empty space? The void between galaxies, the silent space between atoms in your body. According to quantum field theory, there is no such thing as truly empty space. Even what we call the vacuum is a humming, energetic place. The fields are always there, gently vibrating, even in the quietest corners of the cosmos. This leads to the fascinating concept of vacuum fluctuations. These are tiny, spontaneous blips in the fields, brief random changes in energy that pop into and out of existence. It's as if the field twitches a little momentarily, creating a pair of a particle and its corresponding antiparticle, which then quickly annihilate each other and vanish. These flickers don't last long, but their effects are real. They contribute to a tiny force that has been measured between two closely placed metal plates in a vacuum. The vacuum isn't empty. It's gently seething with these ghostly, fleeting particles. This view also provides a beautifully elegant explanation for forces. In classical physics, forces were mysterious actions at a distance. How does the sun's gravity reach out and hold the Earth in its orbit? What carries the message according to quantum field? Theory forces are mediated by the exchange of virtual particles. These aren't real observable particles. They are mathematical intermediaries that flicker into and out of existence just long enough to transfer a force. For instance, when two electrons repel each other, they are not touching. Instead, they are exchanging virtual photons. The electromagnetic force that holds your atoms together is simply the continuous exchange of these silent, ephemeral messengers. Similarly, the strong nuclear force is carried by virtual gluons, and the weak force by virtual W and Z bosons. The universe, it seems, is not held together by invisible strings, but by an endless silent conversation of these virtual messengers. A historical fact about quantum field theory is that its full modern formulation took decades to develop. While the initial ideas emerged in the 1920s to merge quantum mechanics with special relativity, the theory was plagued by mathematical infinities that seemed to make no sense. It wasn't until the late 1940s and 50s that brilliant physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed the technique of renormalization, a mathematical process to handle these infinities. This allowed for incredibly precise predictions and cemented the theory as a cornerstone of modern physics, forming the basis for the standard model of particle physics. It was a long, quiet, and beautiful struggle to find the right language to describe this invisible reality. But this beautiful, elegant theory also leads to one of the most profound and unsettling problems in all of science. According to quantum field theory, all those vacuum fluctuations, all that seething, jittery energy should contribute an enormous amount of energy to space itself. A quirky detail and a major headache for physicists is what they call the vacuum catastrophe. When they try to calculate the amount of vacuum energy, the number they get is staggeringly enormous, so large that if it were true, the universe would have been torn apart instantly after the Big Bang. But our universe is here. The real observed amount of vacuum energy, what we call the cosmological constant, is incredibly small. The discrepancy is a factor of about 1 followed by 120 zeros. This isn't a small rounding error. It's the largest discrepancy between theory and observation in all of science. It is a mystery that still whispers in the halls of physics, and no one has a good answer for it. And this leads to the most important open question in physics, a profound and elegant academic debate. Quantum field theory, in all its glory, does not include gravity. It describes the electromagnetic weak and strong nuclear forces, but not the force that shapes galaxies and stars. The search for a theory of quantum gravity, one that can unify the smooth, elegant curves of Einstein's general relativity with the strange probabilistic world of quantum fields, is the Everest of modern physics. Many ideas from string theory to loop quantum gravity attempt to answer this question, but no one has yet found the complete picture. It's a reminder that for all we know, there is still so much that we don't. But tonight we can rest with the quiet beauty of what we do know. We can find peace in this unifying picture. The universe is not a collection of separate pieces, but a single interconnected symphony of fields. The particles we thought of as the fundamental building blocks are really just the surface ripples of something deeper, something continuous and serene. When you see a spark of electricity, you are seeing a gentle flutter in the electromagnetic field. When you look at the glow of a candle, you are seeing the electromagnetic field in motion. And you in your soft bed are made of these very same fields. Your atoms, your neurons, your thoughts, all of it arises from this quantum field playground. You are not separate from the universe. You are the universe briefly arranged in the shape of a person. Let's take a gentle detour away from photons and particles smashing in sterile labs and into the heart of something far more familiar, life itself. Plants stretching toward the sun. Birds migrating across continents, your own body thinking. Breathing, dreaming, all of it is a beautiful, intricate dance of molecules. But could it be just possibly that life itself relies on quantum physics? For much of modern history, biology and quantum mechanics have lived in separate neighborhoods. Biology, the study of the messy, the warm, the wet, was a world of large molecules and complex systems. Quantum physics, the realm of the cold, the isolated, the unfathomably tiny, was a world of electrons and probability clouds. One deals in blood cells and beehives, the other in wave functions and uncertainty. And yet, over the past few decades, a new field has begun to blossom in the space where these worlds overlap. It's called quantum biology, and while it's still young and full of open questions, it's offering us tantalizing glimpses into how quantum phenomena may shape the very foundations of life. Let's begin our quiet journey with something green: photosynthesis. This is one of the most important processes on Earth, how plants convert sunlight into chemical energy. When a photon from sunlight hits a leaf, its energy must be transferred from one part of the photosynthetic system to another, to a place called the reaction center, where the real chemistry happens. You would think this transfer might be a random walk, the energy bouncing around from molecule to molecule, eventually hopefully hitting the right spot. But experimental evidence suggests otherwise. In some systems, this energy moves with astonishing efficiency, far better than a random bounce and wait approach would allow. So, how enter quantum coherence? Some researchers believe that during this energy transfer, the exciton, the packet of energy created by the photon, doesn't just choose one path. Instead, it explores multiple paths at once in a quantum superposition and finds the most efficient route to the reaction center. It's as if the energy doesn't just roll around. It splits, explores every possible path simultaneously, and then collapses into the shortest one. Experiments using ultra-fast lasers have detected evidence of this quantum coherence, lasting for a surprisingly long time in these systems, even in the warm, noisy environment of a living cell. This is unexpected. We usually think quantum effects are easily destroyed by heat. And yet here they are, quietly helping a leaf turn sunlight into sugar. And this isn't just about plants. Let's turn our attention to the sky. Every year, migratory birds like the European robin travel thousands of miles, navigating with breathtaking accuracy. They don't carry maps or GPS, and yet they seem to know exactly where they are going. A historical fact that has puzzled ornithologists for a long time is how they do this. A leading theory suggests that they can see Earth's magnetic field, and that the mechanism for this is rooted in quantum mechanics. A quirky detail of this theory is that it involves molecules in their eyes called cryptochromes. When light hits a cryptochrome molecule, it excites an electron, creating a pair of electrons that become quantum entangled. These entangled electrons have a quantum spin, which is subtly influenced by the direction of Earth's magnetic field. Depending on the bird's orientation, the magnetic field changes the balance of the electron's spin states, which in turn influences a chemical reaction in the bird's retina. The bird might not see lines in the sky, but perhaps a light or dark spot that helps it orient itself geographically. This is a subtle, beautiful idea, a living creature using the weird, non-local properties of entanglement to find its way home. And what about your own senses? The traditional theory of smell is a lock-and-key model. A molecule's shape fits a receptor in your nose, and that triggers a signal. But there are some molecules that have nearly identical shapes, but smell completely different, and vice versa. This has led some scientists to propose a different theory, a vibrational theory of olfaction that might involve quantum tunneling. When a molecule binds to a receptor, it doesn't just sit there. It vibrates at a specific frequency. And if that vibration matches a specific energy level in the receptor, it can enable a quantum event. An electron can tunnel through a barrier, triggering a signal to the brain. It's like a magical tuning fork. Only when the molecule vibrates, just so does the electron leap through the quantum barrier and send the message, "This is vanilla." This theory is still in its early days and a source of active academic debate, but it's a beautiful reminder that even something as ordinary as sniffing a flower might involve subtle quantum processes. Now let's turn to the most complex biological system. We know the human brain. Could quantum effects be playing a role in your thoughts, your consciousness? This is a highly speculative and controversial area, and one of the most significant open questions in science. The brain is warm wet, and incredibly noisy, a place where quantum superposition and entanglement should not survive for long. The delicate quantum states would be instantly destroyed by the constant interactions. However, some researchers, most famously the physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed a theory called orchestrated objective reduction, or OR. They suggest there may be microstructures inside neurons called microtubules that could be isolated enough to support quantum processes, and that these processes may be linked to consciousness itself. This idea is not widely accepted in the neuroscience community, but it's part of a growing curiosity about whether quantum mechanics might help explain phenomena that classical biology still struggles with. Whether or not consciousness is quantum, the idea invites us to look at the brain not just as a collection of wires and chemicals, but as something deeply interwoven with the laws of physics at every level. And isn't it beautiful to think that your thoughts, drifting gently towards sleep, might be supported by processes reaching all the way down to the quantum scale? Quantum biology is still in its infancy, and many of its claims are still hotly debated. But even the possibility that life relies on these strange quantum phenomena opens up a world of wonder. It reminds us that biology is not separate from physics, that evolution, in its tireless tinkering, may have discovered and refined ways to harness quantum weirdness long before we did. It suggests that inside every leaf, every eye, every breath, there may be a hidden quantum heartbeat. So as you lie, still consider this: the atoms in your body are ancient, born in stars, shaped by chemistry, and now arranged in a way that allows you to wonder, to feel, to be. And maybe, just maybe, part of that being is built not just from molecules and muscles, but from the shimmering dancing rules of quantum mechanics. The rules that let particles tunnel through walls, that let electrons be here and there, that let birds find their way home by looking at the sky and seeing invisible forces. In the end, quantum biology invites us to soften the borders between disciplines and between ourselves and the world, to see not a division between science and life, but a tapestry woven together, atom by atom, wave function by wave function, dream by dream. Now, as we ease into the final part of our journey, let's find a gentle landing. We've explored the strange, the beautiful, and the profoundly quiet heart of quantum reality. We've seen that it's a world built on possibilities, not certainties, and that your very atoms are governed by its rules. We have met particles that are also waves, and we've seen how the simple act of observation shapes their reality. We've watched the silent dance of entanglement, a bond that stretches across galaxies. We've floated through the soft inherent blurriness of the uncertainty principle and discovered that the sun itself owes its life to particles that slip through walls. We've even found hints that life itself, from the green of a leaf to the sense of smell, may have a quiet quantum heartbeat. But with all this wonder, there's a natural tendency to misunderstand, to turn these quiet truths into loud myths. Quantum physics, for all its elegance, has become a magnet for half-truths and misconceptions. So let's take a moment to gently clear the air, to put aside the half-truths and embrace the elegance of what quantum physics really is. The first and perhaps most persistent myth is this: quantum physics says you can change reality with your mind. You may have heard this before, phrased like a cosmic secret: your thoughts shape reality. Or, quantum physics proves that by focusing your intention, you can manifest what you desire. It sounds empowering, and it's a beautiful thought. If the observer affects the system, and we are observers, then surely our thoughts must be powerful agents of change. Right? Well, not quite. The historical fact is that the original theories about consciousness causing collapse were more philosophical than physical, and modern science has largely moved past them. In physics, observation means measurement and interaction between a quantum system and a measuring device. This doesn't require human consciousness. A particle detector, a stray cosmic ray, or even a single air molecule can cause a quantum state to collapse. Your thoughts, however lovely and powerful they are for your own life, do not control the trajectory of electrons or make particles jump through quantum hoops. Reality is not your personal projection screen. It is a shared canvas, and the quantum rules apply equally to everyone, not based on their intentions. The second myth is that quantum entanglement means faster than light communication. This idea has sparked countless sci-fi stories and daydreams. The truth is stranger and more subtle. Yes, the correlation between two entangled particles is instantaneous, but you cannot use that correlation to send information. The reason is simple. When you measure your half of the entangled pair, the result is completely random. You can't control it. So while your particle's state instantly determines your friend's particle's state on the other side of the galaxy, you can't force your particle to be up to send a secret message. You have to wait for your friend to tell you what they got, and that communication can only travel at the speed of light. So while entanglement is a real non-local connection, it doesn't break the universal speed limit. It's a beautiful, mysterious bond, but it is not a quantum walkie-talkie. The third great myth is that Schrödinger's cat is both dead and alive. This is the metaphor that launched 1,000 jokes and perhaps just as many misunderstandings. As we discussed, Schrödinger's thought experiment was meant to highlight how absurd it would be to apply the rules of the quantum world to a large everyday object. A quirky detail about this myth is its stubborn persistence in popular culture, often appearing in places from television sitcoms to self-help books as a literal truth. The reality is that decoherence prevents large objects like cats from ever entering a superposition. The cat is constantly interacting with billions of particles airlight the walls of the box, and each of these interactions instantly collapses any potential superposition. The cat is either dead or alive, long before you ever open the box. The thought experiment is a philosophical tool, not a prediction of zombie felines. The fourth myth is that quantum physics is just random and chaotic. It's easy to hear about probability and uncertainty and assume that the universe is just a cosmic coin toss that anything can happen at any time. But this too is a myth. Quantum physics is deeply, beautifully structured. It is governed by precise mathematical rules and elegant equations that predict the behavior of particles and fields with astounding accuracy. Yes, the outcome of a single event may be probabilistic. You can't say exactly where an electron will land, but you can say with extreme confidence how likely it is to land in any given spot. This makes quantum mechanics not chaotic, but statistical. It's more like a beautifully designed weather system than a roll of the dice. Randomness exists, but it is cradled in order. And finally, the last myth, quantum physics, means anything is possible. This one is often used to justify all sorts of things. Telepathy, teleportation, bending spoons with your mind. The argument goes, if particles can be in two places at once and tunnel through barriers, then surely there are no limits. But this is a grand leap of logic. Quantum physics does allow for strange things, but it also sets very strict boundaries around what's possible. There are rules, mathematical, observable, testable rules. You can't break the conservation of energy just because it feels good. You can't make an electron travel faster than light by wishing on a star. Quantum theory is one of the most experimentally confirmed theories in all of science. It expands our understanding of what nature can do, but it does not throw out logic, consistency, or evidence. If you've ever believed or repeated any of these myths, don't worry. They're popular for a reason. They speak to a desire to feel connected to the deeper workings of the universe, and there's something beautiful in that impulse. But the truth is more magical and more comforting. The real quantum world is far more interesting, more subtle and more full of wonder than any myth could ever make it. And this brings us to a final elegant thought, one that lingers at the heart of the quantum realm and a significant academic debate for the last 100 years. Is there a single objective reality, or is reality subjective, created by the observer? We have seen how the act of measurement changes the system. we've talked about the many worlds interpretation, where every possibility is real, and the Copenhagen interpretation, where nothing is real until it's measured. There is no consensus. There is no one single answer. And in that lack of an answer, in that vast open question, lies the deepest peace, the world you see around you. The classical world of solid objects and predictable motions is not separate from quantum mechanics. It emerges from it. The behavior of large objects arises from the collective behavior of countless quantum particles smoothed out by statistics and noise. The solidity of the table is built on the uncertainty of its parts. The structure of your body is a consequence of electrons bound by the strange rules of the quantum world. So as you lie there relaxing, drifting, let this be your takeaway. The universe is not made of things. It is made of stories of patterns of probabilities. And you, dear listener, are part of that unfolding story, woven quietly, exquisitely into the fabric of reality itself. Your every cell, every thought, every moment is built on particles that behave not like marbles, but like melodies, uncertain, interconnected, and deeply beautiful. Let the final images of this journey gently fade. Picture a soft sea of probabilities, a gentle hum of unseen energy. The world is not rigid. It breathes, it shimmers, it dances between being and becoming. It's a place where even at its most fundamental level, there is a softness to it, a blur, a breath, a margin of mystery. You are not just a conscious observer in a world that is static. You are a quiet, gentle participant in a world that might be dreaming right along with you. Let yourself drift now. No need to hold on to these ideas. The universe has its own way of holding on to you. You are part of the way it unfolds, and that is a truth more comforting than any sleep.